In this video, I will show you the behavior of series RLC circuit. Let's say I have a resistor whose resistance is R ohm. I have an inductor whose inductance is L, and I have a capacitor whose capacitance is C. These R, L and C. See, they are connected in series. Okay, as they are connected in series, this circuit is known as series RLC circuit, and we are applying an alternating voltage V equal to Vm sin omega t in this circuit. You will find the application of series RLC circuit in real life, because every circuit we use contain this series RLC circuit. Every circuit has certain portion of resistance, certain inductance and certain capacitance, or combination of R, L and C. Here we are applying V equal to Vm sin omega t. Let's say the frequency of this alternating signal is equal to F. See, here we are applying an alternating voltage Vm sin omega t. As a result, let's say we get an alternating current I flowing in this circuit. Let's say the value V is the RMS value of applied voltage. The current I is the RMS value of this alternating current I. See, as this is a total series circuit, total current I will be same all over the circuit. That means same current will be flowing through the resistance, inductance and capacitance, and also through this source. So in the circuit we will get the total current I everywhere in the circuit. See, as the current I is flowing in the circuit, the total ohmic opposition offered by the inductance will be XL. XL is equal to twice phi FL, inductive reactance, and the total opposition to the current flow offered by this capacitance will be XC. XC is equal to 1 by twice phi FC ohm. Capacitive reactance is equal to 1 by twice phi FC. As this is a series circuit, current will remain same all over the circuit, but the voltage, this applied voltage, will divide throughout the components. Let's say the voltage VR is the voltage across resistance R, and that will be equal to I into R, Ohm's law. The voltage across the inductor is equal to VL, and that will be equal to I XL, and the voltage across the capacitor, let's see, equal to VC. Voltage across capacitance will be VC, which will be equal to I XC. Now see, as we are multiplying R with RMS value of current, XL with RMS value of current, and XC with RMS value of current, this VR, VL and VC will be RMS quantity. Now see, the current that is flowing through this resistance is I. Let's say the direction of the current is in this direction. As in case of a pure resistance, the current through the resistance and the voltage across that resistance, here the voltage across the resistance is VR, they will be going in the same direction. Let's say VR is going in this direction. Here VR and I will be in phase. In case of this inductor, voltage drop is VL and the current is I. Let's say that current is I and that is flowing in this direction. In case of a pure inductor, current I lags the voltage across that inductor by an angle of 90 degrees. That means if I take I in this direction, VL will be in this direction, and the phase difference between them will be 90 degree. And in case of a pure capacitor, if I take the current in this direction, if I consider the current I in this direction, voltage will be 90 degree lagging from the current. Voltage across the capacitor will be 90 degree behind from the current phasor. or current vector. So here you will see here I will be in phase. Here you will see the voltage across the inductor will lead current I by 90 degree, and here the current I lead Vc by 90 degree. So here we have taken the current I as our reference phasor in this direction. Okay, in all the three cases, see VR and I will maintain a phase difference of 0. They are in phase. Therefore you will see this VR will maintain a 90 degree angle with this VL and with this VC, because they are creating a 90 degree angle with respect to reference axis. Now see, VL is going in this direction with respect to the current I, and VC is going in this direction. That means VL and VC are going in opposite direction. Therefore we cannot take the algebraic sum of VR, VL and VC, as they have created different angles with respect to reference phasor. Therefore we will take the vector sum of the voltages or phasor sum. Okay, now see, this is a closed circuit in which we are applying the voltage V. As this is a series circuit, this V is divided into VR, VL and VC. Therefore if I apply KVL in the circuit in phasor form, I can write it like this. I will apply Kirchhoff's voltage law in this closed loop in vector form or phasor form. I will get applied voltage V will be equal to the sum of voltage across the resistor plus voltage across the inductor plus voltage across the capacitor. Now look at this instant. Here you will see this VL is increasing in positive direction. At that instant this VC is going in negative direction. That means this VL and this VC are in opposite direction at the same instant. Therefore you will see VL and VC are going in opposite direction. So the phasor diagram of this equation V equal to VR plus VL plus VC of the circuit will be dependent on the value of VL and VC, as they are going in the opposite direction, and the value of VL is equal to IXL and the value of VC is equal to capacitive reactance IXC into RMS value of current in this circuit. Therefore you will see, if I consider the value of VL and VC as they are going in the opposite direction, there are three possible cases in this circuit. First one is, if VL, the voltage across the inductor, is greater than the value of capacitor voltage, or inductive reactance has a value greater than the capacitive reactance XC. Number 2, VL, inductor voltage drop, is less than capacitor voltage drop, or inductive reactance is smaller than the capacitive reactance. And the third condition is that VL is equal to VC, capacitor voltage drop is equal to inductor voltage drop, or inductive reactance is equal to capacitive reactance. I will discuss all these three conditions in this video. And this XL equal to XC, or the voltage across the capacitor is equal to the voltage across the inductor, is known as resonant condition of the RL circuit. I will talk about series and parallel resonance in a separate video. Okay, now let me point out each of these three cases. Okay, at first I will show you VL greater than VC or XL greater than XC. After that I will show you VL less than VC or XL less than XC. At last I will show you VL equal to VC or XL equal to XC case in this video. Now consider the first case, when the voltage across the inductor will be greater than the voltage across the capacitor, or inductive reactance will be greater than the capacitive reactance XC. Okay, now see, in this circuit the current I remains same all over the circuit because it is a series circuit. Therefore, we will take the current I as our reference phasor, and I will denote that with OA. Okay, and I will take the reference in the direction of plus x axis. Let's say this OA is our reference axis and it indicates the current phasor I. Now look at this VR. VR is the voltage drop across this resistor R. In a pure resistor, the voltage VR and the reference current I will go in the same direction. Therefore, I will take the VR in this direction or at the direction of reference phasor. So I will denote VR with OP in the same direction of phasor current I. Okay, let's say this OB is our voltage VR. VR is equal to IR. Okay, now see the voltage across this inductor is VL. Okay, and see in case of this inductor, if I take the reference axis in the plus x direction, VL leads I by 90 degree. That means I will take VL in the direction of plus y axis. So as VL is in this direction, I will take VL in this direction and I will denote that with OC. So this OC will indicate VL. Now see the voltage across the capacitor VC. I will denote that with OD. Okay, see if I take the current in the plus x axis direction, you will see VC lags current by 90 degree. That means I will take it in the minus y direction. Okay, therefore I will take VC in this direction in the opposite of VL. In this case, VL is greater than VC, so our OC will be greater than OD, and at this origin this OC and OD are going in the opposite direction. Therefore, the resultant of this OC and OD, let's say I denote that with OE. This OE will be the subtraction of OC minus OD. So let's say OE. This OE is the voltage VL minus VC because OC is equal to VL and VC equal to OD. Okay, now see I get the OE and OB phasor. Our applied voltage V will be the algebraic sum of OB and OE phasor. Okay, now see this is OE and this is OB. If I place an equal vector of OB at this point, or if I place an equal vector of OE at this place, I will get the applied voltage phasor, sum of OB and OE vector. Okay, now see if this EF be the equal vector of OB and the BF be the equal vector of OE, you will see I will get a vector OF, which will be the algebraic sum of OB and this BF. This BF is equal to OE. See, OF will be our applied voltage phasor V. OB is the VR voltage phasor, and the OL vector will be the difference of VL and VC. Okay, so this voltage phasor is VL minus VC, and in this direction I get VR. Okay, now see, this is our applied voltage phasor V. This is our current phasor I. Let's say between V and I we get an angle phi. Okay, now look at the triangle OBF. You will see this angle will be 90 degree. So I will say that OBF is a right triangle. Therefore this OBF will be the voltage triangle for the case VL is greater than VC. Okay, now see, this OB will represent VR. This BF, which is equal to OE, will represent VL minus VC. Okay, now from this voltage triangle I can write down hypotenuse square OF square is equal to OB square plus BF square. OF is our applied voltage V. Therefore I can write V square equal to VR square plus BF equal to VL minus VC. VL minus VC. VR equal to IR and VL equal to IXL and VC equal to IXC. So here I will get I square into R square plus XL minus XC whole square equal to V square. If I take square root, I will get V equal to I root over R square plus XL minus XC square. So the current I in this circuit will be equal to V divided by root over R square plus XL minus XC whole square. This R square, this root over R square plus XL minus XC whole square is known as impedance of the circuit. So I can write it I equal to V by Z, where Z is the impedance of this circuit. The magnitude of the impedance will be equal to Z equal to root over R square plus XL minus XC whole square. Okay, now see, if I put the value of XL and XC here, I will get impedance Z equal to root over R square plus omega L minus 1 by omega C whole square. This is the resultant reactance. So in case of this circuit, resultant reactance will be equal to X equal to XL minus XC, because XL is greater than XC. Here I will get omega L minus 1 by omega C. See, in case of this circuit, VL is greater than VC. So this RLC series circuit will be an inductive circuit. And in case of an inductive circuit, our current I lags voltage V. This I is the current flowing in the circuit and this V is the applied voltage V. See here, look at the voltage triangle. This is our applied voltage V and this is our reference current I. Therefore you will see there will be an angle phi that is created between this V and I, and it is obvious that I lags V by an angle of phi. So I can write down I lags V by an angle phi. The value of phi will be less than 90 degree but greater than 0 degree. As in the circuit, current lags voltage phi. Therefore power factor, which is also cosine phi. This cosine phi will be lagging in this circuit, and the lagging phase angle phi will be equal to tan inverse XL minus XC divided by the resistance R, or I can write it like this: tan inverse resultant reactance by resistance. See, I have deduced all the parameters for the condition XL greater than XC or VL greater than VC. Now I will show you the condition VL is less than VC. Now consider the second case when our VL will be less than VC or XL will be less than XC. That means capacitive reactance will be less than inductive reactance, or capacitor voltage will be less than the voltage across the inductor. As in the circuit, current I will be same all over the circuit, so I will take current I as reference and I will denote that with OA. So let's say this OA is our reference phasor I. Okay, now look at this resistor R. The voltage across this resistor VR and the current through that resistor I are going in the same direction. So because they are in phase, so I will take VR in the same direction as our phasor current I will denote that phasor with OB. So this will be our OB. The voltage VR equal to IR. Now see, the voltage across the inductor VL will be 90 degree ahead of the reference current I. Therefore, if I take I in positive x-axis, I will take VL in positive y-axis or in this direction, such that it creates 90 degree angle. Let's say this is our voltage phasor VL. I will denote VL with OC. So this OC will indicate VL. Okay, now see, the voltage across the capacitor VC will lag phasor current I by 90 degree, or it will create 90 degree angle. If I take reference current I in plus x-axis, I will take VC in minus y-axis. That means I will take VC in this direction. So this OD will indicate our voltage phasor VC. OD will indicate voltage phasor VC. Now see, this OC and this OD are going in opposite direction. Therefore, let's say the resultant of them, I'll denote that with OE. OE will be equal to OD minus OC, because in the circuit VC is greater than VL. So here our resultant will be VC minus VL. Okay, this is our OC or VL and this is our OD. Therefore, let's say this OE indicates our resultant phasor. See, we have OB and OE. Our applied voltage phasor will be the phasor sum of OE and OB. Therefore, if I take the equal vector of OE at this point, or if I take the equal vector of OB at this point, I will get the algebraic sum of OB and OE. Now let me do that. See, if I place the equal vector of OB equal to EF at this point, this OE and EF will indicate OF, which will be the algebraic sum of OB and OE. Or if I place the equal vector of OE at this point, I will get OB plus BF. BF will be equal to OE. So I will get our applied voltage phasor V. Now see, this OE is equal to VC minus VL. Therefore, BF will also be equal to VC minus VL. This will be VC minus VL. This will be the phasor diagram of the circuit. Okay, now see, this angle will be 90 degree, so this will be voltage triangle, because we have drawn the triangle, right triangle, by using the voltage component VR, VC, VL, applied voltage V. Okay, now let me show you the current equation, impedance and the phase angle of the circuit. Here this OBF, it will be a right triangle, and this will form voltage triangle. Here this OB will indicate VR. Okay, OB equal to VR, and this OE, which will be equal to BF, it will be equal to VC minus VL. Now see, in the triangle OBF, as this is a right triangle, I will apply Pythagorean. OF square is equal to OB square plus BF square. Here OF will be V and this OB will be VR. BF is equal to OE, so it will be VC minus VL whole square. V square equal to VR square plus V square is equal to IR whole square plus IXC minus IXL whole square. If I take I square common, I will get I square into R square plus XC minus XL whole square equal to V square. If I take the square root, I will get V equal to I into root over R square plus XC minus XL whole square. So the current equation will be equal to I equal to V divided by root over R square plus XC minus XL whole square. See here, V divided by Z will be our current, where this Z equal to our impedance. Z equal to root over R square plus XC minus XL whole square. Okay, here XC equal to 1 by omega C and XL equal to omega L. Therefore our resultant reactance we will denote that with X, that will be equal to XC minus XL, or 1 by omega C minus omega L. See here, as VC is greater than VL or XC greater than XL, this is a capacitive circuit, and in any capacitive circuit, current I leads V. Now look at the voltage triangle. Here you will see this is our reference current I, and this is our applied voltage phasor V. I leads V by an angle of phi. So here I can say, as this is a capacitive circuit, I leads V by angle phi. Phi will be less than 90 degree but greater than 0 degree. As a result, our power factor, which is equal to cosine phi, will be leading, because in a capacitive circuit current leads V by phi. Now let me talk about the last case, case 3. When VL, voltage across the inductor, is equal to the voltage across the capacitor, or inductive reactance XL is equal to capacitive reactance XL equal to XC. Okay, see here in the circuit I will remain same, so I will take I as our phasor reference, and I will denote that with reference phasor OA. Let's say I take this reference phasor in OA in the direction of plus X. This is our current phasor I. The voltage phasor VR, which will be in phase with I. Therefore, I will denote VR with OB, and this will be in the same direction as our reference current I. Okay, see, VL will create a 90-degree angle with current I. Therefore, I will take VL in this direction. This is OC. VL will be equal to OC. Okay, now see, VC, voltage across the capacitor, will be 90-degree lagging from the reference current. Let's say I denote that VC in this direction with OD. VC with OD. Now see, in this case VL equal to VC. That means this OC will be equal to OD. Therefore, the reference phasor OE will be equal to 0, because OC minus OD will be equal. Therefore, you will see the applied voltage V will be equal to the voltage drop across the resistor VR. As a result, I will get V into IR, or I into Z. So you will see our impedance Z will be equal to R, because the inductive reactance XL gets cancelled by the capacitive reactance. Okay, so this circuit will be a pure resistive circuit, and this is known as resonant condition, because inductive reactance will be equal to capacitive reactance. That's it. Thank you.